All right, this is my lecture on potential energy. This is still in chapter 6, section 6.3. And before I introduce our new topic today, I'm going to just kind of quick review what we've learned to date. We have learned the definition of work with respects to physics is equal to the force times the distance times this cosine theta, where theta is the angle between the force vector and the displacement vector. And the reason why we use this cosine theta is because we want to have the magnitude of the force that is parallel to the displacement. And so that will take care of all of our situations, whether or not the force is parallel to the surface or if it's at some angle. And the units of work is a Newton meter, and we give it a special name, which is called a joule. And this is work is a form of energy. Okay, because we know joules to be a unit of energy. And so when we do work, we're doing what? We're adding energy to the system. Work can be positive if that angle is between 0 and 9 degrees. It can be 0 if it's at 90 degrees, and it can be negative. So we can actually add energy to the system or take away energy to the system, or better yet, do no work to the system, depending on how we apply that force. If we are adding energy to the system, something has to happen. And what happens is we are going to change the kinetic energy of the system or the object. And that equation is 1/2 mv squared. And again, it's in units of joules, as long as we have used meters and meters per second. It is a form of energy, and it is a energy that is related to an object's motion. Okay, so we have the mass of an object times its velocity squared. And we also learned this very powerful theorem, one of the most important ones in physics, and that is the work energy theorem. It states that the net work, or the total work, is equal to the change in kinetic energy. So if I know how much work I have done, I can determine what impact I'm going to have on the kinetic energy. And so if I do positive work, I'm going to increase my kinetic energy. If I do negative work, I'm going to decrease my kinetic energy. Okay. All right. Now it takes us to the next. We have two more energies that I would like to introduce you to. We're going to learn about potential energy due to gravity and elastic potential energy. And I want to show a video that includes both of these, in fact, all three of the energies that we're learning about, because this is around us every single day. So I want to show a video. We're going to talk about what's going on in here as we learn about these energies. So hopefully you were able to see that. I have no idea if that works on my Zoom meeting recordings, but nevertheless. So we have a new type of energy that we may have seen. We have this person that has climbed up a ladder and gone to or brought up to the top of a cliff by a crane. And what type of energy is that person have? They have potential energy due to gravity. So this potential energy is a new energy. It is also in units of joules, but it's an energy that is stored for later use. So this person climbs up to the top of that cliff, and even though she has no kinetic energy, she has gained some type of energy that is stored. She has the potential to do um, something with all that stored energy. This is a perfect storage system. We will never, in the sense that the energy is never lost. Okay, we can't lose or create or destroy energy. So the two types of energies that we're going to learn about is the potential energy due to gravity, which is what the type of energy the bungee jumper had at the very top. And we have potential energy, and we'll call it um, elastic energy, or we're going to learn about it in terms of a spring, but that occurs as well in this video. All right, I needed a person who would like, we're going to have someone come to the front of the room and take a book from the floor and raise the book to as high as they can. And they will have hold the book up, and we ask ourselves, how much work did she do? Well, let's see. We have a force of gravity. I'm sorry, the force that she's applying to the book. And we have the force of gravity pointing down. So we know that she did work. She did this force normal, which is equal to the force gravity times the distance, which we know is going to be mg times that distance. We'll call it h. So this student has done some work by raising the book to some height. And that work now didn't go into changing the kinetic energy, because essentially the book is sitting there at rest at the top of her head. It was that work had to go somewhere, which is still in units of joules. That is potential energy due to gravity that she has created. That work that she did created a potential energy due to gravity. It is related to the object's mass, its gravitational acceleration due to Earth, and the height in which she raised the book. Now, if she raises the book at to a higher height, then the amount of work that she did had to increase, because she went to a farther distance. And sure enough, the potential energy due to gravity also increased. If she raised a book that was twice the mass, she also had to do more work. So the amount of work that she did is related to how high she raised the book and how much the book's mass. And so that work is converted into energy. So it's got to go somewhere. So we're going to store that energy that she created into a new energy called potential energy due to gravity. And its equation is mgh. And once again, it is in meters times kilograms times meters per second squared. And if we look at that, this is a Newton and this is a meter. And so our units again are in joules. Okay, so let's actually work a problem on how to calculate the gravitational energy that is generated or is there. Okay, so basically the example is find the gravitational potential energy of a 65 kilogram person sitting on a diving board. So here is a picture. We have a sketch. They are sitting on a diving board, and we were told that the mass of the person is 65 kilograms, and this height is equal to 3 meters. Now, we've been asked for the gravitational potential energy that this person has. So the equation for that is mgh. So we got to look at this equation a little bit closer. The m is the mass, and that is pretty straightforward. It's the mass of the person. G is the acceleration due to gravity on Earth. And we know that to be approximately 9.8 meters per second squared. And let's talk about the h. What is h? H is the height above or below the reference line, or zero potential energy. So you first have to identify where is zero, your zero reference line. Okay. In this class, we will basically always assume that the zero line is at the bottom of the problem or at the ground. So but there is a potential for it to be below the zero line. And so anyway, there's the reference line. So height in this case is 3 meters. So we will have 65 kilograms times 3 meters times this height, which, or G, which is 9.8 meters per second squared. And we will find that number to be 1911 joules, okay? So the steps involved, again, same steps I always use: sketch, identify what was given, your knowns, identify what they're asking for, and in this case, we need to identify the zero reference line. Okay. Let's do another one. We have a candy bar called Mountain Bar that has a nutritional energy of 8.8 times 10 to the 5th joules. If an 8.1 kilogram mountain climber eats a mountain bar and converts all of its energy to potential energy, what altitude gain can the climber achieve? So we can actually convert food to energy. And they told us that the energy that is in this bar is 8.87 times 10 to the 5th joules. The mass of the mountain climber is 81 kilograms. And we have been told that we're going to convert all of that energy to potential energy. So we know that the potential energy is going to now be the amount that was originally contained within this bar. And they've asked, what altitude can the climber achieve? So they're asking for H. Now I brought this problem up because I want to show something. And that is, well, is it this distance, Mrs. Query, or is it the H? And what matters in this particular equation is only the vertical height. It does not matter how far she traveled in the X direction. We only care about the vertical height. And so we are looking for H, and so we will rearrange that equation for H. And that will be H equals potential energy due to gravity divided by mass divided by acceleration due to gravity. Notice I have no numbers until I'm found what I'm looking for. And now I would plug in my numbers. 8.87 times 10 to the 5th joules divided by the mass, which was 81 kilojoules or kilograms, and 9.8 meters per second squared. Now, since I am in SI units, and I have used all the proper SI units, if I'm looking for height, my unit will come out to be meters. And I find that to be 1,117 meters. All right. There's another type of stored energy. And that is potential energy that is related to elastic bands, springs, anything that can essentially change their shape after being distorted. Okay, so for example, a bouncy ball that has, if you can imagine in slow motion, the ball is, as it falls and hits the ground, it compresses, and that ball now has stored energy because it wants to go back to its original shape. So stretching, in order for us to actually deform or change the shape of that, we actually have to do work. So I have some examples here. I have like a rubber band, a slingshot, a spring. I have to do work to actually create that distortion of that object. Well, that work is an energy, is a form of energy, and that energy that I have created by doing that work is stored in this object. And we're going to call this the potential energy that is due to elastic. It's elastic potential energy. The ones that we're going to focus on in this class are potential energy due to a spring. We're only going to work with a spring. So again, this is energy that is stored from work that I have done on an elastic band or a spring or some other object such like that. And so we will focus only on springs in this particular course. So the definition for potential energy due to a spring is equal to 1/2 times that spring constant times the distance or the stretch or compression. So here we have our new equation right here, and it is 1/2 K times X squared. Let's look at the units. Well, what is a K? That is newtons over meters. What is X? That is in meters, and we're going to square it. And so one of my meters cancels, and I am back to a Newton meter, which is again a joule. We got to talk about what each one of those terms are within that equation. K is the K constant of the spring. It's related to the property of the spring, and X is the distance away from its equilibrium. So let's figure out how to use that. Here is an example. I have a spring with a K constant of 120 Newton meters. I'm going to stretch it a distance of 0.23 centimeters. The question is how much potential energy is stored in the spring. So I have potential energy due to the spring is 1/2 K times X squared, and I have plugged in 120 Newton meters, and then I am going to plug in 2.3 centimeters squared. Anyone have a problem with what I got there? And I equal and I find that to be 317.4. And that is actually would be wrong. And why is that wrong? Because I did not convert centimeters to meters. And so we will make sure that we convert centimeters to meters. 0.023 meters. We will use 0.0 correct units so that we get the answer in correct units, and that will give me 0.5 times 120 times 0.023 squared equals, and I get the answer 0.02, or sorry, 32 joules. Okay, there we go. One more, and then I have assignment 6.2, which is essentially the ones that we just completed, but also the problems at the end of the 6.2 lesson check. So how far, so they're asking for X, must a spring with a spring constant of 85, so that the spring constant is 85 Newton meters, be stretched. So we want to know X in order to store the potential energy of 0.22 joules. So I have my equation, which is equal to 1/2 K times X squared, and I want to know what X is. So I have to rearrange this equation to get X by itself, and I will find that to be 2 times the potential energy due to a spring divided by K, and that is 2 times 0.22 joules over K, which is 85, and I will find that X value to be equal to 0.07 meters or 7 centimeters. All right, that's my lesson for today. There are numbers 32 through 36 that are part of the assignment for today's lesson.